In this tutorial, we will explore the concept of closures in Lua through a practical example. Closures are a powerful feature in Lua that allow functions to retain access to variables from their containing scope, even after that scope has exited. We will delve into three different counting functions: CounterA, CounterB, and CounterC, each showcasing a unique aspect of closures. By the end, you will have a solid understanding of how closures work in Lua and how they can be utilized in your own projects. First, we define a function named CounterA. This function does not take any parameters. Inside the CounterA function, we declare a local variable named count and initialize it to 0. This count variable will be used to keep track of our counting. We then have a for loop that iterates from 1 to 5. In each iteration of the loop, we increment the count variable by 1 using count equal to count plus 1. We print the current value of count, and finally, we call the CounterA function. This execution of the function causes it to go through the steps defined above, resulting in the count from 1 to 5 being printed along with CounterA in front of each number. In summary, CounterA is a user-defined function that encapsulates a for loop. It defines a specific behavior, counting from 1 to 5 and printing each count along with a label. This encapsulation allows you to easily reuse this behavior whenever you call the CounterA function in your code. Next, we define a function named CounterB. Inside this function, it initializes a local variable count to 5. The CounterB function returns an anonymous function. This returned function captures the count variable from its containing scope due to closure. Inside the returned function, it increments the count variable by 1. Then, it returns the new value of count, calls the CounterB function and assigns the returned function to the variable b. Executes a for loop that iterates from 1 to 5. In each iteration, it calls the function stored in the variable b, which increments count and returns its value. Prints the current value of count after incrementing, along with the string CounterB. So, in summary, CounterB is a function that returns another function. The returned function has access to the count variable from its enclosing scope and increments it each time it is called. Then, the main block calls this returned function 5 times and prints the increment values. CounterA is called only once because the loop is encapsulated within the function itself. Each time you call CounterA, it executes the loop inside it, counting from 1 to 5 and printing the values. In contrast, CounterB is called once to obtain the inner function, which is then called 5 times in a loop. Each time the inner function is called, it increments the count variable and returns its value, effectively counting from 6 to 10 and printing the increment values. In CounterB, the returned function forms a closure by capturing and retaining access to the count variable declared in the enclosing scope of CounterB function. This allows the inner function to maintain and increment the count variable across multiple calls, creating a persistent state between function invocations. We start by copying the structure of CounterB to create CounterC. We add a parameter starter to CounterC, which allows us to specify the starting value of the count. Initializing the count variable inside CounterC, we initialize the count variable with the value of the starter parameter. This means that the count will start from the value provided as an argument when calling CounterC. The returned function from CounterC still behaves the same way as the one from CounterB, incrementing the count each time it is called. When calling CounterC with parameter 10, for example, the count will start from 10 instead of 5 as in CounterB. This modification allows for more flexibility in choosing the starting value of the count. So, in summary, by adding a parameter to CounterC, we enhance its versatility by allowing users to specify the initial count value, providing more control over the function's behavior. Our last function CounterAll serves as an example of function composition, combining all three counting functions in one place. Because of the different scopes of CounterA, CounterB, and CounterC, different variables are used to call each function within CounterAll. This highlights the modular nature of functions in Lua and how they can be composed together to achieve more complex behaviors. CounterAll demonstrates how to utilize and compose multiple functions together, each with its own scope and behavior, to achieve a desired outcome. Closures grant functions access to variables from their enclosing scope, even after that scope has exited. In simpler terms, a closure closes over or captures variables from the environment in which it was defined, allowing the function to retain and manipulate those variables later on. This feature is particularly useful for creating functions with persistent state, as demonstrated in our examples. By capturing and retaining variables from their surrounding scope, closures enable functions to maintain state across multiple calls, making them powerful tools for managing data and behavior in Lua. This tutorial provided a practical exploration of functions and loops in Lua, showcasing their utility in various scenarios. Through examples such as CounterA, CounterB, and CounterC, we demonstrated how functions can be used to encapsulate behavior, while loops allowed for repetitive execution. Additionally, the concept of closure was introduced, highlighting its role in combining functions and retaining state across multiple calls. We also explored function composition, exemplified by the CounterAll function, which combines multiple functions to achieve complex behaviors. By understanding these fundamental concepts, Lua developers can enhance their ability to write modular, efficient, and flexible code.